Okay, imagine that you've been approached with a new design project, and the project is to design a noise machine that's used for people while they sleep, or kids, specifically babies. And when you start looking at this design project, one of the things you might want to consider is just different ways to generate noise. And so it's very useful to use some approximation and some instrumentation, some calculations to evaluate different design options. So in this case, we are going to look at two different ways to generate noise, at least commonly used. And the first is just a traditional fan. So some people might turn a fan on and then just let it generate its noise, and you don't necessarily need the cooling, but you're just using it for the white noise. And the second device we're going to look at for generating white noise is actually a purpose-built noise machine, and it's essentially just a little speaker that plays different sounds that are white noise. We're going to compare these two. We're going to look at a couple different things. The first is how much electrical energy it consumes, how much each of them consume. And to do that, we're going to use this kilowatt, which allows you to plug a device in, and it will tell you how much power is being consumed, amperage and other things too. We're also going to use an app for your phone, and it's called Arduino Science Journal, and that we're going to use to measure the sound output from these two things. So we're going to compare the sound and the energy used, and it just allows us to explore the design space a little bit and try to understand, just approximate, which one is better in terms of energy and sound and trade-offs and things like that. So I'll first start with the regular fan. And then I'm going to turn it on to low, and then I'm going to take a recording for 5 seconds. Okay, and I'm going to save that as fan low. And then I'm going to go ahead and take another measurement on medium. Okay. And then one last one on high. Okay, here are the three measurements that I made. Fan low was an average of 53.8 decibels. On fan medium, the average was 58.8. It's shown in the middle there. And then on fan high, the average was 61.2 decibels. And I just want to enter each of those values into this spreadsheet that I have. You can go inside and analyze each of these recordings. It's kind of cool. You can hit play and it will replay and show you the entire measurement. So now I'm going to then go through the same sweep and understand how much energy is being used, so electrical energy. So for this, I have to, I have the fan plugged in, and I want to click on the watts, and it'll show how many watts are being consumed. And right now you can see there's 27.2 watts. So I'm going to enter that into my spreadsheet. For low, I'm going to type in 27.1. And then I'm going to go to medium. And you can see here it's about 31.8 watts. And then I'll go to high. And it's about 41.1 watts. Okay, now I'm going to do an experiment very similarly with this noise machine here. And I'm going to have it plugged in, as I do here, to this kilowatt, so I can measure how much power is being used. So I want to click on the watt button to read out watts. Like before, I open the app, I go to the little microphone, and I'm going to turn it on. And I'm going to want to adjust the intensity of this to try to match the medium setting, which was like 58, 59 decibels. I'm going to go ahead and take a 5-second average to see, make sure that it's about right. And what we can see for power is we're consuming about 2.8 watts. So I'm going to put 2.8 into my spreadsheet. Okay, so here's a spreadsheet where I was putting in all of my values as I was taking measurements. And here's the data here for the fan measurements. So I put the fan on low, medium, and high. And for each of those, I use the app, the Arduino Science Journal, to measure the sound output using the little microphone in decibels. And then I used a kilowatt to measure the power, the electrical power, in watts. So this is the data that I had written down, and then I did the same thing for the noise machine. And these were the values. You can see right away that the noise machine is significantly less power for the same amount of decibels, roughly. So that's kind of interesting. It's about a factor of, the fan is a factor of about 11 times more electrical power is needed. So let's calculate how much more energy would be needed for the whole year and cost, because that's in terms of design, that's often what you're trying to understand is either the environmental impact in terms of CO2 or the cost and things like that. So to calculate that, I needed to come up with some constants over here. So I wanted to understand how many hours per day the fan or the noise machine would be used. And I estimated that it'd be about 12 if you're using it for a small child. I mean, usually a baby will sleep at least 12 hours per day, including naps. And then you can multiply that number, 12 by 365, to get the total number of hours per year. So then if I come over here, I can calculate the watt hours per year for the fan. Watt hours is a measurement of energy, and how you calculate it is you just multiply the watts, the energy or the power being used, and you multiply it by the hours at which that power is being used. So over an entire year, it would be 31.8 times the number of hours that it's used that year, and that ends up being this number here. And to calculate the cost per year for the fan, you need to know what the cost is per watt hour, because I just calculated the watt hours here. And so that's what I have over here. So I looked up online what the cost in terms of cents per kilowatt hour. It's about 15.79 cents per kilowatt hour in Madison. And then I converted that to dollars per watt hour just by dividing by 1,000 to convert from kilowatts to watts. And then to convert from cents to dollars, I had to divide by another 100. So that's what's shown here is I take this 15 cents per 7.9, I divide by 1,000 to convert from kilowatts to watts, and then I divide by another 100 to convert from cents to dollars. And so then I have the dollar per watt hour, and that's what I need here. Here's how many watt hours of energy are used over that year. And if I multiply that by the dollar per watt hour, I get here that it costs about $22 per year to run that fan. I can do the same measurements here or calculations for the noise machine, instead using the noise machine number. So it's 2.8, which is how many watts it would use multiplied by the hour. So that's ends up being this number here in terms of watt hours per year. And then the same thing with cost is that you take this dollar per watt hour, you multiply that by the number of watt hours, and it's about $2 per year to run that. The difference in annual cost, so you basically take the difference between these numbers and you get about $20. So it costs $20 more to run the fan as the noise machine as compared to the noise machine itself, the little speaker. You might also want to calculate the CO2 generated, the difference. So you might say, hey, this product has this amount of CO2 generated or environmental impact, and this other product or architecture has a different, has this environmental impact. And to do that, what I did is I took the difference in watt hours and I multiplied by a number I found online, which is the pounds of CO2 generated per watt hour of electricity, assuming that you're using coal to generate the electricity, which is kind of the worst case scenario. So you can see here after 1 year that the difference would be about 280 or 281 pounds of CO2 generated, more than the noise machine itself, just using the little speaker. So it's interesting, these numbers, like I said, plus these experiments using these quick sensors will give you the ability to trade off those things and try to understand the design and different approaches you could use. And a lot of time in design, you're making these kind of decisions early on. You want to explore different ways of generating noise, let's say if you're making a noise machine. Beyond these architectures of either using a fan or a little speaker, there are a lot of other design choices that will be needed, like the user interface, in general, the way that the user interacts with the product. But this is at least showing you how you can use some quick and dirty experiments and some quick calculations to provide a more quantitative analysis or an estimate of how one design differs from another design choice. So another interesting thing to do is to compare the type, quality, or intensity of the sound coming out of both the fan and the noise machine. And you can see here in the summary, here's the fan low, fan medium, and fan high. And you can see that the minimum and maximum, the difference between those tends to be about roughly 20 decibels. So there's, kind of the peaks and the troughs, the highs and lows vary by almost 20 decibels. So that's pretty much the same for both the fan, medium, and high. You can also click in here, which is kind of interesting. And you can drag around with your finger and analyze the noise using the app. So that's the fan. Like I said, it's about 20 decibel difference. If I go into the noise machine, you can see the difference here is much less. It's like roughly 10. And so I think to me that says that the noise machine, if you're kind of comparing the noise machine versus fan, another difference is that the noise machine tends to have less variation with the intensity. So it's a little bit of a smoother output, which may, it may have an impact. It probably does on quality for sleep in general, but that would be kind of a separate study. But it's interesting that you could have this quantitative difference to show how the noise output is different and the variation is different from one to the other. And you can analyze the data using this app.